Welcome to the 2020 DMD virtual conference. My name is Tom Secord. I'm an assistant professor at the University of St. Thomas in mechanical engineering. And today I'd like to discuss our work on developing an integrated I2C sensor network for transcatheter heart valves. So it all begins with a background in TAVR technology, which is transcatheter aortic valve replacement technology. So shown on the slide is a healthy aortic valve. Now, as we age, that valve becomes calcified, and if that calcification deposit is too severe, the valve becomes stenotic and can't open and close properly, at which point one of two interventions is required, either surgical replacement or transcatheter replacement, which is becoming increasingly desirable. So through a catheter, a physician can place a shape memory alloy frame as well as bioprosthetic leaflets that are sewn into that frame, and that takes over function for the diseased valve. This is a purely mechanical and passive device. However, by virtue of being in the thoracic cavity, in the ascending aorta, that valve is really quite close to a lot of useful signals: pressure, acceleration, respiration, pulse wave velocity, ECG impedance, biological measures, and the ubiquitous vital sign of heart rate. So our goal in this work is to bridge the gap between these two things and actually create a sensor network within the transcatheter valve frame that can measure some or all of these signals. So a little more detail on that idea. Using the same catheterization setup as the TAVR procedure, a physician could then place another catheter that contains the appropriate sensors, and those sensors are placed at strategic landing zones within the frame to connect to the sensor network. And this creates a very modular system that can be customized to the patient needs. For our initial illustration, we're going to use an IMU and specifically pull out the acceleration signals. And to really demonstrate the network capabilities, we're using two sensors, one at the inflow and one at the outflow of the valve, to measure a time-delayed acceleration as you would observe due to a pressure pulse that travels up the aorta. So we call this measurement pulse wave velocity, which is an important diagnostic and prognostic indicator. The I2C network, or I2C network, is very cleanly integrated into the frame, and it's a ubiquitous method for communicating to multiple slaves on a network using only two signal conductors, a data line and a clock line, as shown in the schematic. Additionally, it really does lend itself well to this closed cell structure, provided that you insulate the conductors at the appropriate nodal junctions. In the paper, we show that it requires less energy to communicate across sensors than Bluetooth Low Energy, and we consolidate all of the wireless transmission to a single point on the frame. Additionally, it's a fast enough protocol that you can measure things like the pulse wave velocity and differential pressure measurements across the valve. Just a brief synopsis of our approach to frame design. We designed a 2D cut pattern in CAD, cut that with a laser cutter, wrap it on a mandrel, and then apply the appropriate conductors and dielectrics to create the network. So a schematic of that is shown here as, again, a flat pattern with the sensors on various landing zones. Shown in this small thumbnail image is a wireframe version of this. And you can see on this image, although it's small, the two sensor boards that house the IMUs. And that brings us to a discussion of our approach to sensor design.
So I'm Lucas Koerner, an assistant professor in electrical engineering, and we used IMUs for mobile phones because they serve our purpose well since they're miniaturized, low power, and have an I2C interface. To demonstrate our concept, we designed a custom circuit board that hosts a 3-axis accelerometer and a 3-axis gyroscope. In addition to the IMU, we have bypass capacitors and connections to that frame. The board size is less than ½ an inch on each side, and was actually larger than needed for the electronics to fit the components because it just needed to fit in this 2:1 scaled stent model. So we connected two PCBs to the IMU and then placed voice coil motors at each accelerometer to tap the accelerometers. And at each time difference between the taps, we measured acceleration versus time. And then the delay between these two accelerometer traces was estimated from moving window cross correlation. As shown in the panel on the right now, the estimate of the transit time, calculated from the accelerometer measurements, compared to the program VCM delays with a slope of 1. So we estimated an error in our velocity measurement of 0.2 meters per second, which allows for very good clinical diagnostic accuracy. And then finally, some future work. The backside of our board includes a liquid compatible pressure sensor, and then also developing the processes for fabricating these sensor networks and investigating IMU features.